In this screencast, we're going to look at hydrocarbon functional groups consisting of alkanes, alkenes, and alkynes. So hydrocarbons are nonpolar molecules typically isolated from petroleum, and they serve many important purposes in society. So, for example, octane is used as fuel for combustion engines, and acetylene gas is used in oxy-acetylene torches for cutting metal. So we're starting with very simple hydrocarbons, again, only CC and CH bonds. We're going to see that we can have three different types of carbon-carbon bonds, whether they be carbon-carbon single bonds, carbon-carbon double bonds, or carbon-carbon triple bonds. And the presence of any of those will give us an indication of what type of functional group we're looking at. So as we look at visualize structures, we're also going to look at molecular formulas and make connections between if a molecule is saturated or unsaturated and what those terms mean. And then as we progress through our understanding of hydrocarbon structure, we're going to look at how we can extract a piece of information called the degrees of unsaturation, either by visually looking at the structure or through the molecular formula. And ultimately, what we intend to do is, from a molecular formula, propose different possible constitutional isomers that could belong to that molecular formula, and then differentiate them using the concept of uniqueness. So the key concepts and lecture learning outcomes for this lecture are you should be able to identify all sigma and pi bonds present in a hydrocarbon. That's simple visual inspection. Define the characteristic features present in an alkane, alkene, and alkyne. So we'll look at bond lengths, hybridization, bond angles, things of that nature. Categorize a hydrocarbon as an alkane, alkene, or alkyne. So again, that's a visual inspection. Define the general molecular formulas for the hydrocarbon functional groups of alkane, alkene, and alkyne. Again, that's very important information, and from that we can extract a lot of things, a lot of details, specifically to calculate degrees of unsaturation of any given molecular formula, and then propose reasonable structures based on that information, and just to gain a general understanding of the importance of hydrocarbons in modern civilization. So let's go ahead and dive into this, and I'm going to first show you the three general categories here of hydrocarbons. So we have alkanes, alkenes, and alkynes. So alkanes end in ane, alkenes end in ene, and alkynes end in yne. So even just by the name, we can infer what functional group is present. So we're going to start just by looking at C2 hydrocarbons of each of these types. So I'm going to draw the C2 hydrocarbon alkane, which is ethane. And so that would be a typical bond line formula for ethane, but I want to go ahead and actually put in the hydrogens. And I'm going to do so using the wedge dash convention as well. So again, each carbon has 3 hydrogens. So what I've done, and what I'll highlight in red here, the bonds that I'm drawing in or over highlighting in red, those bonds are in the plane of the screencast. So they all sit in a plane, and then these bonds, which I'm going to go over in blue, these wedges, those are coming out towards you. And then in green, these dashes, they are going away from you. And so the reason I'm drawing them like that is because we said that the molecules have a 3-dimensional shape. And due to the hybridization, that's a better way of representing what those carbon H bonds look like. So alkanes have sp3 hybridized carbon. So each carbon is sp3 hybridized. And so that means the carbon has tetrahedral geometry. And the typical bond angle for three elements is usually 109.5 or thereabouts. So if we have HCC, so this bond angle, we can say is 109.5. So let's put down some more information before we move into the alkenes. So again, I said the name of this compound was ethane. In there we see that ANE ending. If we count the carbons, we have 2. The hydrogens, we have 6. That gets us a molecular weight of 2 times 12 is 24, plus 6 times 1 is 6, so 24 plus 6 is 30. So I want to point out now for alkanes, what is the general molecular formula for an alkane? So if we're given any alkane, it's going to have a general formula of CN H2N plus 2. And I want to highlight that in yellow because we're going to use this formula quite a bit over the course of this semester. So again, this is the general Alkane formula. So what do we mean by that? So for what we see with ethane, when n equals 2, we plug in 2n plus 2, that gets us 6. So just to show some physical properties here of ethane, the melting point is equal to negative 172 degrees, and the boiling point is equal to negative 88. So at room temp, this is a gas. So again, we can explain from prior lectures why it is a gas. It's a nonpolar molecule. There's not a lot of intermolecular attractive forces. Because of that, the molecule basically it boils at a very low temperature, so negative 88. Let's go ahead and move on now to alkenes. In the alkene that I'm going to draw here, again, we're keeping with 2 carbons. The name of this alkene is ethene. Again, that ends in ene. So alkenes have a pi bond. So there's our carbon-carbon pi bond, and then that would be a valid bond line structure for ethene, because it's implicitly understood that each carbon is now bearing 2 hydrogens because we've explicitly shown 2 bonds. Let's go ahead and draw those hydrogens in. Again, I'm gonna show the hydrogens coming out towards you with the wedge. And the the hydrogens going away from you as the dash. So a couple notable things here. The hybridization of each carbon has now changed to sp2. The bond angle of HCC has now changed to 120 degrees. And so why is that? That's due to the hybridization. So the molecule is essentially flat, and the carbons are trigonal planar geometry. So now if we count, we still have 2 carbons, Now we've reduced the number of hydrogens, so we have 4. So we can look at the molecular weight of ethane was 30. We're taking away 2 hydrogens, so the molecular weight of ethene is 28. The general alkene formula is CnH2n. So some physical properties. The melting point is negative 169 degrees. The boiling point is negative 104. So at room temp, this is also a gas. So I want to introduce 2 new ways of classifying things. So alkenes are typically called saturated, and alkenes are unsaturated. So what does unsaturation mean? Unsaturation is in the sort of strictest sense, it's a carbon that does not have the full number of hydrogens bonded to it. So if we look at ethene, our first alkene we're studying here, we can see that the presence of the pi bond, so this double bond, which is equal to a sigma bond plus a pi bond. The pi bond is what we refer to as unsaturation. Alkynes are also unsaturated. So again, one of the things I really want to point out and make you cognizant of is the general functional group name has characteristics present in it. So alkene, alkyne, there's unsaturation. And that's important for us when we're proposing structures for unknowns. So let's stick with the C2 alkyne. So this is ethyne. So again, it ends in YNE. Now I'm gonna show the carbons. So we have a carbon-carbon triple bond. And so we're showing 3 bonds to carbon. So we have 1 remaining bond to show, that's to hydrogen. Now these carbons are at different hybridizations. These are called sp. And so the bond angle now changes. This bond angle is 180 degrees. And so these type of carbons have a linear geometry. So what's the molecular formula? C2H2. We've removed 2 hydrogen atoms from ethene to ethyne, so now we're at a molecular weight of 26. You can see the general formula for an alkyne is CnH2n minus 2. The melting point of acetylene is negative 81. The boiling point is negative 84. So that may seem a little strange. This molecule actually sublimes, so it doesn't really go through a liquid state. So at room temp, this is equal to a gas. So any sort of physical data, you will be given that physical data. It's not terribly important that you spend mental energy trying to memorize those numbers or anything. If you were given a series of compounds and associated melting points and boiling points, you might be asked to rationalize what the trend present is based on the functional groups within that series. So other than that, you don't have to memorize things. Really, that's not the point of this class. So in this slide, what I want to talk about now is the degrees of unsaturation and why that's important to us in learning organic chemistry. So we said that a pi bond is an unsaturation. Another type of unsaturation is a ring. So let's just jot that down. So a pi bond or a ring. And the way that we can understand that is in both of those functional groups, the carbons do not have the maximum number of hydrogen atoms bonded to them. So in given this molecule here, which is called ethyl estradiol, this molecule is known as a steroid, and the steroid nucleus, as I'm going to draw in red, has 4 rings. So the A ring, the B ring, the C ring, and the D ring. So just through visual inspection, we can see that this molecule has 4 rings. And so each ring is a degree of unsaturation. So let's go ahead and now highlight the pi bonds present. So we have 1, 2, 3. Now we have a triple bond, so we have 4, 5. So we have So we add those two together, that's 9. So the total degrees of unsaturation for this molecule is 9. So again, why is that important? Because the degree of unsaturation gives us some sort of clue as to what functional groups can be present. So what I'd like to do now is to determine the molecular formula for ethyl estradiol. So let's do a carbon count. So we have, we'll just go ahead and number these as we go. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we count 20 carbons. Let's go ahead and do the same for the hydrogens now. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So we have H24, and then we have 2 heteroatoms present, oxygens, so O2. So what we're going to learn on the next slide is that we can take this molecular formula and just given the molecular formula, calculate what the degrees of unsaturation are. So initially we just did it through visual inspection by counting the rings and counting the pi bonds, adding those together, we got 9. The next way we're going to do it is given the molecular formula, we can go through an algorithm and we'll actually calculate the number to be 9. So in this slide, we're going to calculate degrees of unsaturation using the general alkane formula of CnH2n plus 2. And again, as a reminder, for an alkane, this molecular formula is fully saturated. Notice there's no heteroatoms present, it's just carbon and hydrogen. From the prior slide, we found that ethynyl estradiol has a molecular formula. So I'm going to say given of C20H24O2. So again, aside from visual counting of rings and pi bonds, the molecular formula can be used to determine the degrees of unsaturation. So let's go through this algorithm here. Given a structure, determine the molecular formula, so we did that. All heteroatoms must be counted as hydrogens according to the following. We ignore oxygen. So what does this become? We're ignoring oxygen. It's going to be C20H24. Nitrogens, subtract 1 from the hydrogen count. We don't have any nitrogens present. Halogens such as fluorine, chlorine, bromine, or iodine will add 1 hydrogen. So we don't have any of those. So essentially we're at this revised formula, and that's what we're going to use. So we're there. Now determine what the molecular formula should be based on n number of carbons. So here we have n equals 20. So what is the fully saturated alkane? So again, we're using the formula CnH2n plus 2. We've found n is equal to 20, so we plug that in there. Let's do the simple math here. So for 20 carbons, we should have 42 hydrogens. C20H42. We have C20H24. And so we're going to do just a bit of math. The carbons we're going to subtract out. And at this point, we're left with H18. So what we've done is subtract the saturated alkane molecular formula from the revised. The number will always be an integer. That's what we found, 18. And we're going to take 18 divided by H2, because H2 is what we are considering to be an equivalent to a degree of unsaturation. And so when we do that, 18 divided by 2, we find that we get 9. And so that's what we found in the prior visual inspection as well. So just let's review that again. We said we had 1, 2, 3, 4 rings. One, two, 3, 4, 5 pi bonds. Again, that totals to 9 degrees of unsaturation. So we've done it visually, and we've done it with the algorithm shown on this slide. So basically, we've sort of tied the two together. We have 9 degrees of unsaturation, 4 of which consist of rings, 5 of which consist of pi bonds. And the reason this information is useful to us is because we can then differentiate how each carbon will react under various reaction conditions. So in this last slide of the lecture here, let's consider the prompt where you're given a molecular formula C4H8, and you're asked to draw all the possible constitutional isomers in a bond line convention. So the first thing that you should do anytime you're given a molecular formula is determine if there is a degree of unsaturation or multiple degrees of unsaturation present. So what you want to do is recall CnH2n plus 2 is the general formula for a saturated alkane. So we're given C4H8, so we're given N equals 4. We plug that in, we have C4H2 times 4 plus 2. So for 4 carbons, the molecular formula should be C4H10. And again, that's fully saturated. So what do? We take our given molecular formula and we subtract that out. So the C4s will cancel each other out. And now we're left with H2, so 10 minus 8 is H2. 1 degree of unsaturation is an equivalent of H2, so that gets us 1 degree of unsaturation. So now we have some information here. With the molecular formula C4H8, we know that within that there is 1 degree of unsaturation. And we know that a degree of unsaturation is either a pi bond or a ring. So we want to, in a very logical fashion, propose all the possibilities for the structures that could have that molecular formula. And let's do the following. We'll create a couple columns here. Here we're going to say pi bond, and then over here we're going to say ring. So that's going to count for the degree of unsaturation. Since we have 4 carbons, let's start with C4. I'm going to put that in this first row here. So C4. So I'm just going to draw 4 carbon atoms. There they are. Now, under the first column, pi bond, we have to put a pi bond in that molecule. So let me go ahead and put some numbers here. 1, 2, 3, 4. And to do this logically, let's just put the pi bond between 1 and 2. This molecule is an alkene. It's a 4-carbon alkene, so it would be a butene. And the location of the pi bond starts at 1, so we're going to say this is 1-butene. So you can ask, well, why didn't you put the pi bond between carbons 2 and 3? We can do that as well. So now that's a different compound, and we have to name it different. So the pi bond now starts at carbon 2. So this is 2-butene. But there's also a geometrical isomer to 2-butene. And I'm going to draw the following. So this is also 2-butene. But how do we differentiate between these two if they both have the same name? The first one has the descriptor of trans. See these terminal methyl groups at positions 1 and 4? See how they're on opposite faces of that alkene? That's how we call this trans. Trans means opposite. In here, the methyl groups 1 and 4 are on the same side, so we call that cis. So for the pi bonds, those are the only possibilities we can have. 1-butene, trans 2-butene, cis 2-butene. What about a ring? If the degree of unsaturation is present in a ring, a 4-membered ring is called cyclobutane. So we've exhausted all the C4 possibilities. So we can go down now to C3 possibilities. So these are basically going to be propane or propene derivatives. So we're at the 3-carbon nomenclature at this point. So let me do the following. I'm going to draw the 3-carbon linear. Now we have two things to do. We have to put in a pi bond and we have to put in a methyl group. We cannot put that methyl group at positions 1 or 3 because then that gets us to the linear C4 chain. So the methyl group has to go at position 2. Now the pi bond, we have no, based on the way this molecule is drawn in the symmetry present, we have no choice but to put it between 1 and 2. We can put it between 2 and 3, or the methyl group at 2. We're still drawing the same molecule. So because this molecule is now a 3-carbon unit, we're going to name it 2-methyl propene. So notice with these alkenes, they all end in ene. So the ring is a cycloalkane. So we have no other C3 alkene isomers we can draw. There's only one. So what about a C3 cycloalkane? We can draw that. There's cyclopropane. We have 1 carbon to put in. So if we number, we would call this 1-methyl cyclopropane. So notice the nomenclature, because these do not have a pi bond, they have the ane ending, but they start with cyclo, cyclobutane, cyclopropane. So we've proposed 6 constitutional isomers for this molecular formula. So we differentiated them according to their names, obviously, but what about the unique type of hydrogen? So 1-butene has 4 unique type of carbon. Trans 2-butene has 2 unique type of carbon, as does cis 2-butene. 3-methyl propene has 3 unique type of carbon. Cyclobutane has 1 unique type of carbon. And 1-methyl cyclopropane has 3 unique type of carbon. So in blue, I'm going to do the hydrogen now, and then the ratios. 1-butene has 5 unique type of carbon. And let me draw in these hydrogens so that you can see why it's 5. We have a methyl group. We have a methylene group. Then we have this CH. And now this alkene sp2 hybridized carbon, even though it has 2 hydrogens on the same carbon, they are both different because they have differing relationships to the existing H here. So that relationship is different from this relationship. So that's how we get a total of 5. Trans 2-butene, we have 2 unique type of H in a ratio of 6 to 2. The same thing for cis 2-butene. For cyclobutane, the ratio is 1 and the total is 8. For 2-methylpropene, let me draw these hydrogens in. Those hydrogens now are actually equivalent. So our ratio here is 2 unique sets, 6 to 2. Then finally for hydrogen, for 1-methyl cyclopropane, we're going to have 3 unique sets in a ratio of 4 to 3 to 1. Notice that the sum of the hydrogen ratios is always 8. And that will always be the case. That ratio should always total what you see in the molecular formula. If there is symmetry present, the unique sets can be less than what you see for carbon or hydrogen. So again, to wrap up, this has been a screencast explaining the hydrocarbon functional groups of alkanes, alkenes, and alkynes. We've looked at the concept of degrees of unsaturation both visually through calculating a formula, and then we've done a problem where we've proposed constitutional isomers given a molecular formula.